Today's topic is a very important one in linear algebra. Now, this was bugging me a lot when I studied, and today I want to go into a bit of explanation on this one. This is the exchange lemma, or the Steinitz exchange lemma, by the name of Steinitz. I have seen it is also known by the name of the replacement theorem or the replacement lemma. Lemma, as it is useful in proving many important results of this field of mathematics. So what does it say? The statement goes like this. Let V be a vector space over a field K. K is a field of scalars. Now, let U1, U2 up to UN, these n vectors, let me denote it by giving a bar on them so that just to distinguish from the scalars. You don't need to do that. So these n vectors be a basis of the vector space V. Okay, and also let V1, V2 and going on to Vm be a set of m vectors are there, m linearly independent vectors in V. The lemma states that there are two parts actually. The first part is m is less than or equal to n. The second one is, it says that it is possible to replace or exchange, whatever you call, m vectors of, let's call the basis capital B, of B by these vectors. That is, you are replacing m vectors out of this by these vectors, so that these vectors together with n minus m vectors of B form a new basis of the vector space V. Okay, bit confused with all the notations? Okay, let us go back to basics, or shall we say basis. What is the basis of a vector space? It is a subset of the whole vector space which must satisfy these two properties. They have to be linearly independent. It's absolutely necessary. Linearly independent. We'll say Li, whatever. And it generates the whole space. What does it mean? It means that any element of V can be expressed as a linear combination of the elements of S. There won't be any elements for which you won't be able to do this. So, or in other words, they can say that span of S is V, or S spans V, right? Now, whenever I go through concepts like this, it's sometimes important to go back to the most simplified version that you can get. And what would that be? The 2D space in this case. Okay. So you already see I have marked two vectors. Can you identify them? Yes. This is the vector. Now, by vector, you can think of them as like this, directed line segments. Or most of the time, it is easier if you just look at the tip of the arrow, tip of this line segment. That is, what does it give you? It gives you a point. You must have heard the term position vector in some other field. This is actually the vector. So if I call this one, so this is the point definitely 1, 0, and this is the point 0, 1, and they form the conventional basis of the two-dimensional plane, right? So this is also known as sometimes j cap, and this is known as I cap, the vector. But in a sense, they're just points 1, 0 and 0, 1. Now look at any other point. For example, this, I don't know what it is, maybe something. This is also a vector. This is nothing but the line segment going up to this point, right? So what does it mean? That this is any vector of this plane or this vector space of 2 dimensions. You can get it by, look at this one, if you multiply it by some factor which goes up to this, you can do that. It doesn't have to be an integer, it can go up to this, right? And you can multiply this vector 0, 1 vector by some factor going up to this, okay? And it be, say, ai, the whole one, and this whole one, it be maybe j cap. So ai cap plus bj cap, what does it give you? Remember the parallelogram rule. So this gives you the diagonal, which is nothing but the point vector r chosen randomly. Now this you understand. But what if we replace one of these vectors, j cap as it is, and we replace I cap by this fellow? What could this point be? Maybe 3, 1, say. Doesn't matter. 3, -1 it should be. It's in this. So now let this be your v vector. This is still j cap. Okay. Now you have the same point here. Can you express this as a diagonal of some parallelogram whose sides are nothing but sides scaled from these two vectors? It is possible. When you can scale up, you can obviously scale down. When you multiply by a factor maybe less than 1, this one, maybe you get something up to this. Maybe that is your some factor p. So this is pv, and you scale this one, this j cap vector, by a factor q, this q j cap. Now if this is a parallelogram to adjacent sides, you know that by the addition law, this diagonal is nothing but your r vector again, the same r vector. So it is possible to replace one vector. We can clearly visualize in reality. It's always easy to use 2 dimensions for this purpose. Now we had already replaced this one vector I cap by v vector. Now let's also replace this one by this fellow. What shall it be? Maybe minus 0 point something 2, 0.8, say. It can be anything. Just to make it clear to you, it can be anything, as long as they don't coincide, as long as they are not collinear, which is in a sense what we call linear dependence. So these two red lines have to be linearly independent. Now think of the same point or the same vector r that we were dealing with here and here, the same r vector. How will you get this? The idea is same. Maybe we take some factor right? What shall we name it? Maybe R V, and this new vector, let it be W. So this scaled version of W, let it be S into W. So now when you consider the parallelogram law, maybe you will get something like this. So if you add these two vectors, so clearly R can be written as RV cap plus S RV plus SW, right? So it's something like this. This could also be written as a linear combination of I cap and J cap. In terms of different bases, it can be written as a linear combination of V cap and J cap, changing one more vector in the basis or replacing by a new vector. It can be written as a linear combination of these two vectors. R and S are scalars. Okay. R and S are scalars, that is, in this case, just real numbers. Now, let us consider a vector space V over a field of K, and let B be a basis of this vector space. So, if the dimension of the vector space V is n, there will be n vectors in the basis of B. Now, think of any non-null vector belonging to the vector space, right? So since this is a basis, this fellow can be written as a linear combination of these guys. So these can be written as using this form. I hope all of you understand it. For some scalars, AIs, I equals to 1 to n. Now this is obvious, right? Now it's a non-null vector. So obviously there has to be one of these fellows whose coefficient AI is non-zero, right? So at least one of AIs is not zero. If let it be AK or something like that, right? But we don't like this. I mean, it is fine, but we want to rearrange this stuff. So A1 U1 plus A2 U2 plus going up to AK UK plus again going up to AN UN. That AK UK, we somehow renumber it and bring it to the front. Make it U1. So the coefficient which is non-zero, so we can say this process renumbering. Renumbering, let A1 not equal to 0. Note that no generalization is lost in this case. So what we can do, the trick is, now the vector V which we just took is A1 U1 plus the others, right? A2 U2 plus A3 U3 plus AN UN. So it's I equals to 2 to n. Now I was just demonstrating this example for this renumbering thing. So this is non-zero, remember. So by dividing by it, and we want to make this the subject of the formula. So what do we have? Bringing on to this side is v vector minus right. As this is non-zero, what can we do? We can write the u1 vector as 1 by a1 times v minus 1 by a times all these a2 u2 plus a3 u3 plus a n u n. I goes from 1 to 2 to n in this summation. So our job here is done. See, we have already replaced this u1 vector. There is one vector starting from this basis. Now the basis has changed. In place of u1, what will you write? This whole thing. It looks a bit odd, strange to write this whole thing, but actually this has worked. So I can say that this has been replaced. Right? If you want to be more clear, I'll demonstrate with an example. Right? Let w be any vector in V. What does it mean? W can be expressed as a linear combination of these vectors. Now, to write it in general, it can be written as summation of bi ui, where I ranges from 1 to n for some scalars b1, b2 to bn. Now, what is this ui? Ui is changed now. So, w is now b1 u1. In place of u1, what shall we write? We write this big fellow, big thing. Right? So 1 by a1 times v vector minus, include this constant inside the summation coefficients. So we have this, and the other terms are simply I equals to 2 to n. So b2 u2 plus b3 u3 up to bn un. So summation bi ui. All right, now looks clumsy. We can simplify it in a moment. We'll see how it looks like. So let's keep this aside, the v vector. Now the other vectors starts from u2 to un, and same goes in these, right? So what will we do? Can we pair the like terms? Of course. It's as basic as middle school algebra. So for we have inside the summation minus ai by I plus bi. You notice what we have done here? We have taken the coefficients from here, from each ui, and added up to the coefficients of that ui from here. So ai minus negative of ai by a added to bi for each ui, where I runs from 2 to n. u1 is already replaced, remember. Now, any better way of making them look? Yes. Let's write them c1 v vector plus summation I equals to 2 to n ci ui, where what we have done here is basically this b1 by u1, we have named it c1, and each of these thing we have named it ci. Now the vector w, any vector, is written as a linear combination of v vector. What is v? V was this one, and the other remaining vectors of the basis. So what we have done is we have replaced u1 vector by v. Just to demonstrate it more clearly, I have done this calculation. This result we just proved can be called the simple replacement lemma, where we are replacing one vector out of the basis. So now if you look at the Steinitz exchange lemma, it is nothing but a more generalized version of the simple exchange lemma, right? We are talking about m vectors to be replaced, right? So let's go into the proof. I'm sure it looks a bit more understandable now. So let k be any natural number ranging from 1 to m. So you understand where we are going? Yes. We want to apply induction, mathematical induction. We prove by mathematical induction on this k. Mind you, the range of k, of course. So what is our step 1? Step 1 is for k equals to 1. Do we need any proof? Well, we have just done it, right? Follows from simple exchange lemma, which we just proved for one vector. Result is true for k equals to 1. What is the step 2 of any mathematical induction? The inductive hypothesis. So let's take to be k equals to k, right? For some k ranging from less than m. Of course, you know why we have taken it, because the next step we will be proving for k equals to k plus 1, right? So the result is assumed to be true. Mind you, what does it mean? So it means that we set v1, v2 up to vk is linearly independent and k is less than or equal to n, and what do we have? This v1, v2 up to vk, then comes the vectors that were already in the basis, so following k vectors, so uk plus 1 up to un. This is a basis of v. Note that for the starting step, this result obviously follows from, as we said, the simple exchange lemma, and 1 is less than m, so that is also holding true, right? So this is our inductive hypothesis. Now the most important step, proving the result for k equal to k plus 1, right? So v k plus 1 is any vector of v. This means vk plus 1 can be written as a linear combination of vectors of the basis, which means this one, right? So if we want to write it, first there comes the k v1, v2, vk vectors. So 1 to k, this one, plus k plus 1 to n. Then comes the u type vectors. So uk plus 1, uk plus 2 up to un. Right. Now, here is the important claim. we claim that at least one of a k plus 1, a k plus 2, a n, that is from here, must be non-zero. What is the reason for this claim? Let's understand. What if, or if not, if they were not, that would imply that vk plus 1 can be written as a completely as a linear combination of v1, v2, vk. That would mean v1, v2, vk, and as vk plus 1 is written as the linear combination, so vk plus 1 is linearly dependent, which is a contradiction as scale is the name, so which is a contradiction, right? So our claim is true. Obviously, at least one of these has to be non-zero. Now once again we apply that renumbering thing, so that we just get the very first one of these, after reordering the first one of this as non-zero, right? So after reordering, we can assume that only a k plus 1 is non-zero. If a k plus 1 is non-zero, then we can apply that same thing that we did for u1 here in this case of uk plus 1. So vk plus 1 is this summation of ai vi's, where I ranges from 1 to k, plus this a k plus 1 uk plus 1. This is the fellow we will replace, plus the others. So it goes from k plus 2 to n, I equals to k plus 2 to n. So we are planning to replace this. Can we do that? Definitely we can. We can simply write that uk plus 1 can be written as, after dividing by this, remember this here is non-zero, right? So after making this the subject of the formula, so what do you have? You have 1 by ak plus 1 times vk plus 1 minus 1 by ak plus 1 times summation ai vi, I from 1 to k, minus 1 by ak plus 1 sigma ai ui's, where it's from k plus 2 to n. So what we have done, we have, like we discussed, replaced this by this whole thing, whatever it is. The idea is now this is in terms of this vk plus 1. Also from this claim, which we have proved to be true, that one of ak plus 1, ak plus 2 and ak plus n, out of these must be non-zero. It clearly indicates that k plus 1 is less than or equal to n. So that is one part of the claim for n plus 1, and the other part we have just proved, right? So if you name this 1, this is 2. That means, what does it mean? It means that the result holds for k equals to k plus 1. So by the principle of mathematical induction, what can you say? The result holds for all k less than or equal to m. This was the thing we started with. So this completes the proof, right? And this result is used in proving many important other results of linear algebra. So thank you once again.